In this example, I'm going to use the question given, and I'm going to show both methods of working out the force and the angle alpha. In the first method, we're going to solve the way that we've been taught and learned so far, and that's by resolving forces. Okay, so we will choose our line of action and we will split up the forces into their different components and resolve vertically and horizontally. In the second method, I'm going to show you how by using Lami's theorem we can, in certain problems, cut back significantly on the amount of work that we need to do and solve the problems much more quicker and more efficiently. So if we have a look at the question here, the first method I'm going to use is to solve by resolving, and we need to choose a line of action, right? We could keep the line of action horizontal and vertical, but the force that we're trying to solve is force F, and in order to make our lives easier, we're going to resolve with force F being, or the line of action being perpendicular to force F. All right, and so I'm just going to draw that in quickly. So there we have the line of action, and we can see that force F is now perpendicular to that line. Now, just for the sake of it and for demonstration, I am going to extend force F, and we can see that that is perpendicular to the line of action. Now, usually you would draw your components of your forces on the diagram itself, but to make it easier and to a little bit less confusing, I'm just going to draw them off to the side. So if we rotated this diagram around, we could say that force F could be the vertical component up. Then we have the 40 newtons force over here. Now we need an angle, and we can use this angle inside here. Right? The total angle between 40 newtons and F newtons is 120. Our line of action is going to be a perpendicular line, so it's 90 degrees. So we can work out this angle as 120 minus 90, which is 30 degrees. So this angle inside is 30 degrees. Looking at our 50 newtons force, right? That's this one over here. Again, we don't know the angle alpha, all right? And so we'll just have to give this another name. We can call this angle theta, right? And you can see that angle alpha is just angle theta that we've now just made plus 90 degrees, right? That 90-degree angle from the line of action. On my components here, this means this angle here is angle theta, right? Now we need to split our forces up into their components, right? So I'm going to find the horizontal force for the 40 newtons, right? And that's going to be 40, right? It's the adjacent side, so it's going to be 40 cos 30 degrees. And similarly, the vertical component will be equal. It's the opposite side, so it's going to be 40 sine 30 degrees. In the same sense, we're going to resolve these forces here. So x2, the horizontal component, is equal to 50. It's the adjacent side, so cos, and I don't know, this is angle theta. And the vertical component will be 50 sine theta. Now we have an unknown angle and an unknown force to resolve for. So we're going to resolve for the unknown angle first. Okay. And the easiest way to do that is to just solve horizontally at the moment, because that eliminates, in the vertical component, we also have that upward force F, which is also an unknown. So one unknown at a time, let's resolve horizontally. In the horizontal direction, we can see we have two horizontal forces, x1 and x2. And because we are in equilibrium, we can say that these two horizontal forces must be equal to each other. Okay, the net of force is 0. So x1 is 40 cos 30 degrees, and x2 is 50 cos theta. Right, and now we can just solve for theta. So we can take 40 cos 30 degrees on our calculators. We can divide that by 50, and then we can take sine inverse of our answer, and that will give us our angle for theta. Right, so theta is equal to 46.14622, etc. And usually in our exams, we are going to round to 1 decimal place. So theta would be equal to 46.1 degrees. Now keep the number in your calculator because we can already do the next step and solve for alpha. We said that alpha is equal to theta plus 90, so just punch 90 into calculators and you'll get alpha equal to 136.1 degrees. Right, now we can resolve for the unknown force, right? And to do that, we can solve vertically. Okay, because of our line of action, we can resolve the force without having to make two simultaneous equations and combine them. So if we look at the vertical components, we have force F, and then we have the y components of our 40 newtons and 50 newtons. The force F is acting in one direction, and the other two forces are acting in the opposite direction. So if we add these two forces in the vertical direction up, they should be equal to the force in the opposite direction. Again, because our forces are in equilibrium. Right, force F is what we're trying to solve for. Solve force Y1, the vertical component of the 40 newtons is 40 sine 30 degrees. And the vertical component of our 50 newtons is 50 sine theta. Theta is our 46.1 degrees solved in the horizontal component. Now, when you use or plug in that value there, make sure you use the exact value from your calculator. If that means having to go back and recalculate theta to get the exact answer, remember with trigonometry, even the smallest decimal place can make a big difference to the final answer. Okay. So from here, I'm going to solve for force F. Okay. Now I still have my 136.1, all the decimals in my calculator. So in order to calculate theta again, I'm just going to take away 90 degrees. That's going to have me, or give me theta on my calculator. So I'll put in 50 sine, my answer from the previous question, and then I'm going to add that to 40 sine 30. Right, this is going to give me 56.055, etc. Right, and usually at this point we'll round to 3 significant places, so that'll be 56.1 newtons. So this is the way that we have learned previously how to solve these questions, right? Selecting the appropriate line of action. Usually the line of action is going to be perpendicular to the force we're trying to solve. This eliminates us having to split the unknown force into 2 separate components and then having 2 unknowns to solve for, right? So by selecting a line of action that's perpendicular to the force, we are more easily able to resolve. Now, that was one method. Let's have a look at the method that we learned today, and that's Lami's theorem. Okay, Lami's theorem being the one that was derived from the sine rule. So having a look at the diagram again, we're going to relabel everything. Okay, and I'm just going to give them, we have alpha, and I'm going to call this side A, and we have side alpha, right? And I could give all of these names. This could be side B, and sine or angle beta, and then side C, and angle gamma. Just to label them so that if you are trying to compare them to Lami's theorem, the sine rule, you know which angles and which sides go together. Okay? So if we have a look at Lami's theorem, okay, it says that if we take side A over the sine of the angle opposite from it, right? So that's the angle created by the two other forces, right? That's equal to B, right? Over sine beta. So again, we are comparing alpha and the angle opposite from that force, and beta and the angle opposite that force. Okay, and we can say the same thing about the final vector, right? So C over sine gamma. Right, that's Lami's theorem, and now we can use that to solve the problem. So at this point, we don't really, I mean, if we understand how to use Lami's theorem, we don't have to label the sides. We just need to understand where the relationship of these two comes in, right? That the force is being, and the ratio comes from the force and the angle opposite that force. So in the question given, we've been given two force angles, and we've been given one of the angles. So we have two forces and one angle, and we're asked to solve for a force and an angle. So if we look at the force that we're trying to solve for, this force here, right, we have an unknown angle as well. So we have two unknowns. So before we can solve for this force, we need to work out what this angle is. And the easiest way to do that is to solve for alpha, and then using 360 degrees, we could solve for beta. Okay. So to solve for alpha, we're going to look across, and we're going to see we know the magnitude of the force across from the angle. And then we're going to look around at the other forces, and we see we have a force and we have an angle as well. So using Lami's theorem, we can say that if we take that 50 newtons, right, and we divide that by the sine of the angle opposite, which is 120 degrees, that should be equal to, right, we are resolving for alpha, so this is 40 newtons over sine alpha, okay? Now, this is an equation, so the unknown that we're trying to solve is on the denominator, so we're just going to take the reciprocal of everything. So we can rewrite this as sine 120 over 50 equal to sine alpha over 40. Okay, that's going to give me sine alpha. If we put this now into our calculators, we'll take sine of 120. We'll divide that by 50, and we'll multiply it by 40, and that'll give us 0.6928, etc. Right, to solve for alpha, okay, we're going to take sine inverse of the answer, and that's going to give us 43.8537, etc. degrees. Now, in the previous way, you'll notice that we solved alpha by getting 136.1 degrees, but now we're getting 43.85 degrees. So are we doing something wrong? And the question is, well, the answer is no, right? We need to remember where we derived Lami's theorem from, and it came from the fact that it was actually a sine of 180 minus theta, right? And that comes from the fact that the sine, right, sine is positive in both the first and second quadrants, okay? So this angle alpha, which we've gotten now, right, is exactly the same. We'll get the exact same value for sine if we took 180 degrees minus alpha, because sine is positive in both the first and the second quadrant. And just visually from the diagram, we can see that this is not an acute angle. It is the obtuse angle. The obtuse angle sine, unfortunately, because it is positive in the first and the second quadrant, and because we can have angles in a triangle between 0 and 180 degrees, we need to remember that sometimes when we take sine inverse, we need to look at the context it's in, right? And in our case, we can see this is not the acute angle, it's the obtuse angle. So very easily, we just take 180 degrees minus our answer, and that's going to give us our 136.146, etc., which we can simplify into 136.1 degrees, okay? Because we usually round degrees to one decimal place. So just with 4 lines of working out, we were very quickly, without having to resolve any forces, we were able to solve for alpha. Now, because we have alpha and because it's already in our calculators, right, we can already quickly work out the angle opposite the unknown force, this what I've labeled as beta, so this angle over here. These 3 angles must add up to 360 degrees. So we can take 360 minus 120 minus the answer in my calculator, and this is going to give me 103.85, etc. degrees. Now I'm going to keep that in my calculator because obviously I want to use the exact value when I solve for the force that we're trying to resolve. So this force, right, using Lami's theorem, divided by the sine, right, of the angle opposite it, which is this 103.9 degrees that we've just worked out. That must be the same as this, the length of the side, or the magnitude of the side, and the angle of one of the other 2 vectors. Okay, now I'm going to use the one where we know the exact value. That's 50 over sine 120, and we can just resolve the force by multiplying this sine over here and taking it to the other side. So the way I do this in my calculator, right, is I'm going to take the sine of my answer. That's going to give me some value, and I'm going to multiply that by, and I'm going to open brackets on my calculator and go 50 times, or sorry, not 50 times, 50 divide by sine 120, close the double bracket, hit equal, and I'm going to get 56.055, etc. This is a force. We're going to round to 3 significant places, so 56.1 newtons. Okay? So in 3 lines, well, actually 2 without the rounding, but in 3 lines in total, we've resolved and found force F. Okay, and if we compare that to the original one, okay, there was a lot more working out required in order. We had to split components up. We had to find an angle to find our alpha, and then we could only resolve force F, right? It took much more working out. I think I spent 70% more time speaking than the actual time it would have taken me to solve the problem just using Lami's theorem. So 4 lines to solve the angle, 2 lines to solve the force. So hopefully you can see why it is so useful to know this when you're dealing with 3 forces in equilibrium.